Hello everybody and welcome to the latest instalment of ASEG Webinar series. Today it's hosted by the SANT branch and we've got a talk by Teagan, Blaikie and Helen McFarlane about interpreting high resolution aeromagnetic data to aid mapping, undercover and structural analysis of the Tanami Region and Northwest Aileron Province. I've had a sneak peek of this talk, at least some of it, at our session GabFest here in the NT, and I'm looking forward to it. Just a few housekeeping things before we start. Always thank you to our corporate members and our branch sponsors. Today we'll have questions at the end of the session. Go through the questions as per usual in a Zoom meeting, type them in, and at the end I'll select some of the best ones and present them to Teagan and Helen. In our webinar series, coming up, we've got Richard Blewett next on the 30th of March, followed by Jack McCubbin. Richard, of course, has a lot of experience at Geoscience Australia. That'll be a very interesting personal reflection. And Jack's a smart guy who can talk about how gravimetry is helping with geodesy for those who are interested. Please join the Australian Society of Exploration Geophysicists. It's a great organisation. Some of the member benefits there. Of course, the best one is the access to the annual wine offer. But maybe that's just my opinion. Of course, free membership also for students and half price for retirees and recent graduates. And by all means, keep in touch. We've got social media. There's a lot of great videos on YouTube now. Of course, a big presence on LinkedIn, Twitter, Facebook, their website, and monthly emails, newsletters. And at that point, I'll finish the introduction and hand over to Teagan and Helen for the talk. Enjoy.
Okay, thanks Matt for that introduction. So this afternoon, Helen and I are going to be talking about and presenting a bit of a snapshot of some interpretations we've produced across the Tanami Region and Northwest Aileron Province, and this is part of a collaborative project between CSIRO and the Northern Territory Geological Survey. So just to start off with a few acknowledgements, I mean, this work wouldn't have been possible without a collaboration with the NTGS and a few key people there that have really helped out with this work. So Tanya, Barry, Joe, Dot were all incredibly helpful with the geology and the geophysics in bringing this project all together. And Mick was great in compiling all the background data that is fed into this project. Also at CSIRO, we've had a lot of GIS support from Tanya and a lot of support on the geology from Suzanne, who's worked in the area as well. So geophysical data has enormous value in covered terrains and is an effective tool for geological map production and structural analysis. It's incredibly valuable because it can help to connect and extend our observations from areas of really sparse outcrop and sparse drill core coverage to covered areas. And the interpretation importantly helps provide context for other geoscientific studies and can feed into numerical modelling and 3D modelling, for example. So just a bit of an overview of the project and some of the things that Helen and I will be discussing today. So this project involved a lot of processing of both new and legacy geophysical data acquired by both government and industry. And then Helen and I have been working on this to produce a new solid geological and structural interpretation of the region, constrained by some petrophysical data that was available. And we've also undertaken some forward modelling and interpretation of some of the deep seismic data in the area. So the purpose of this work was to interpret the newly acquired geophysical data and produce that solid geological interpretation with the aim of identifying areas that could be targets for follow-up mapping. So there are some questions that have come up as part of this work that we haven't necessarily been able to resolve, but that was sort of part of the aim of this and things that can be worked on in future. So the Tanami region is located in Northern Australia, and it comprises Paleoproterozoic, metasedimentary and volcanic rocks that have been extensively intruded by granites. And this area preserves a really important record of basin development, multiple deformation and metamorphic events, and extensive magmatism during the time the North Australian Craton was assembling. The area is also highly prospective for gold and preserves a number of deposits located in the Tanami, the Dead Bullock Soak, and the Granite goldfields. So although not unique to the Tanami area, this area is quite extensively covered by sedimentary rocks from younger sedimentary basins and by regolith. The rocks we're trying to target in this interpretations are the ones shown in these largely purple polygons here, and you can see that their outcropping extent is quite sparse across most of the interpretation region. And this has led to some uncertainties in what rocks are there and their stratigraphic relationships. So on the right-hand side here, we've got a figure of the stratigraphy and several different stratigraphic schemes that have been put forward by various authors over the years. And one of the big points of contention in the stratigraphy relates particularly to the Mount Charles Formation and where it sits, so whether it sits above the Ware Group or within the Tanami Group, as some of the later work has shown. And there are some differences in the structural schemes put forward by each of these works. So what we're aiming to do from this interpretation is test each of these hypotheses, try and come up with a structural framework and understand where things might sit in the stratigraphy and see if we can resolve that in the geophysics. So just looking at the stratigraphy in a little bit more detail, this area comprises two main groups, which is the Tanami group, consisting of iron-rich siliciclastic and chemical sedimentary rocks, and these have intercalated and intrusive mafic volcanics, which transition to more siliciclastic sedimentary rocks towards the top of the sequence. Overlying the Tanami group is the Ware group, which is largely comprised of felsic volcanic rocks and siliciclastics with some minor mafic volcanics, and these were deposited during a widespread episode of volcanism. In intruding these two groups is some widespread granite intrusive rocks, and these are grouped into three main suites, being the Grimoire, the Frederick, and the Birthday suites. So although this area is extensively covered by younger sedimentary basins and regolith, the area is very well imaged in geophysical data. And this includes a new survey recently acquired by the NTGS, which is shown by this black outline here, which was acquired at 200-metre line-spaced resolution. And within that, there are several areas of 100-metre line-spaced infill, which were sponsored by industry. In addition to that, there's over 70 aeromagnetic surveys that have been acquired by industry that are open file and of equivalent or higher resolution to the newly acquired survey. So as part of this project, we have conducted an audit and have reprocessed all the available industry data as well as the existing government acquired aeromagnetic data, and reprocessed these and applied a number of filters to try and enhance the signal related to the geology and aid in the interpretation process. So on the left-hand side, this is the new aeromagnetic survey. This is the reduced to the pole data with just a sun shadow on it, enhancing the shorter wavelength information. On the right-hand side is just an example of some of the routine filters that we have applied. including first and second vertical derivatives, tilt derivatives, analytical signal, just to name a few. And so all of these filters were applied to every industry data set and all the government acquired data sets across the area. And this is all fed into the interpretation. So some of the industry data in this area actually dates back to the late 80s and early 90s, but it is an incredible source of information and provides increased resolutions in areas of high structural complexity. So on the left-hand side here, we've got the new 200-metre survey acquired by the NTGS, and on the right is a compilation of some of the industry data acquired at 50 to 100-metre line spacing. And you can just see the enhanced resolution you have in this area of really high structural complexity, which has really helped resolve some uncertainties in the interpretation of folding and fault overprinting relationships. So straight up, I'll show you the new interpretation derived from this. So on the left-hand side, we've got the aeromagnetic data, and on the right-hand side is the solid geological interpretation. And as we progress through the talk, we'll have a look at a few key areas in a bit more detail. But just as a broad overview here, you can see these red units here are the major granites that are intruding the Tanami and the Ware groups. You can see they're ringed by these magnetic units related to the Tanami group, surrounded by contact aureoles. You can see the large amount of structural detail we've been able to incorporate into this, particularly related to some brittle faulting and some shear zones down here in the northwest Aileron Province, and a lot of later faulting and overprinting of these granite intrusions in this area here. So this interpretation was mostly derived from the aeromagnetic data. It's constrained by where there is some outcropping geology or where there is drill core. And they have been points of truth in the interpretation that has then been used to extend this undercover. So in most of the areas, we've been able to attribute the geophysical signal to a known lithology, but there are parts of the interpretation where there's no outcrop at all. And there is some uncertainty in some of the mapped units that are maybe points to follow up in future mapping if any outcrop can be identified, or in future drilling campaigns. So there are still some uncertainties in this interpretation that have come up as part of this work. So as a comparison to what's come out of this study here on the right-hand side and some of the interpretations that were produced back in between 2000 and 2005, when the NTGS last focused on this area in some of their regional mapping campaigns. And you can just see here that the added value that this new geophysical data has brought to this area in terms of being able to add a lot more structural information in this area and improve clarity on some of the units that we're mapping. So in addition, this map here shows the near surface geology. So if you were to strip off cover, what was underneath that, and includes interpretation of the Birrindudu Basin as well. But as part of this work, we've also stripped that off and interpreted the deeper basement geology and extended the interpretation of the Tanami group under the Birrindudu Basin towards the northwest. And we've also made some interpretation of some deeper granite bodies down here in the south on the margin of the Aileron Province as well. So some of the constraints that have fed into this interpretation and also to the forward modelling that we'll talk about later in the talk is there was some petrophysical data that was compiled from measurements taken by the NTGS and also from industry reporting, and this is taken from NTGS's database. There is petrophysical data, which includes density and magnetic susceptibility for most major lithologies in this area. However, some units are better represented than others just due to the nature of industry targeting certain rock types in this area during exploration. So just having a quick look at the petrophysical properties for the major units mapped in this area. So the dead Bullock and the Mount Charles formations within the Tanami group, comprising iron-rich siliciclastic chemical sedimentary rocks with intercalated volcanics. This group, or these formations, tend to have quite a high magnetic susceptibility and a very high density. They have quite similar characteristics, so they are the blue and red coloured bars on this histogram. They have quite similar petrophysical properties, and that makes them difficult to resolve from each other purely based on petrophysics. The Callie formation does have a slightly lower density and a much lower magnetic susceptibility compared to the dead Bullock and the Mount Charles formation. The intrusive suites being the Grimward and the Frederick suites, which were the two suites that we had the petrophysical information for. There's sort of not really any surprises here. These petrophysical properties are quite characteristic of granites, so quite low density. The Grimward suite has a much lower magnetic susceptibility, though it's got a little bit of a range, whereas the Frederick suite has a low density, but it has quite a moderate to high magnetic susceptibility. And this is the key feature in distinguishing these two suites from each other in the aeromagnetic data. So having a look at some key areas in a bit more detail and looking at the geophysical response. This image here shows the Tanami group in the areas surrounding the Camarian-Frankinia dome, crossing the Tanami and the Granite map sheets. You can see here you've got the granites from the Camarian-Frankinia domes defined by a low gravity anomaly, low magnetic response, and they are ringed by the magnetic stratigraphy of the dead Bullock formation. You can see here we've got the Mount Charles formation on here following the cursor. On the right hand side here we've got the dead Bullock formation on the eastern side of the granites. These two units, they've got a similar magnetic intensity, but they've got a subtly different texture. The Mount Charles formation tends to have a really tight fabric of linear anomalies, whereas the dead Bullock formation is typically more broader spaced magnetic anomalies. This is a pattern we see across this area. So that was the key, although they've got similar petrophysical properties, that was the key difference in distinguishing them in the interpretation. The Ware Group showing the sedimentary rocks within the Ware Group, typically defined by a moderate magnetic intensity. We've got the Wilson formation here. We can see a little bit of folding within the group, and the Century formation here, which has a more slightly bit more subdued compared to the Wilson formation, and a bit more of a sort of stippled irregular texture and less banding within it as well. We've got this area, this uncertain area on the map here, which we're not really sure if it's related to the Century formation, or whether it's possibly related to the Callie formation, or potentially just some magnetic regolith in this area here. So that was just sort of an uncertain area of the interpretation here. The volcanic sequences within the Ware Group tend to be restricted to the northeast of the interpretation area in the Tanami map sheet. So we've got the Nanny Goat volcanics, which is characterized by these linear magnetic highs through here. The Mount Wainneke formation tends to be quite irregular. This sort of stippled texture, it can be quite, it's been subjected to a lot of brittle faulting. And you've got the Wainneke granifier, this intrusion here, with a moderate magnetic signature and a smooth response. In Central Mount Solitaire, this shows, this image here shows the typical characteristics of the Callie formation. Is sitting at the top of the Tanami Group and the land and rock formation of the Aileron Province. These units are typically thought to be correlatives of each other, and they've got quite similar responses in the geophysics. So we see more of a transitional relationship to them. We don't see an abrupt, necessarily an abrupt contact between the two formations. It seems to be, at least in this area, transitional. In here you can see you've got the magnetic, these linear magnetic anomalies, which are related to the dead Bullock formation, and you're getting more irregular, this irregular texture, which tends to be associated with some of the granites in this area here. As part of this interpretation, we did redefine the extent of the Billabong Complex. So this is Archean complex that has a little bit of outcrop, but is otherwise not really well constrained in its extent. Based on the limited outcrop, we've been able to correlate with this arcuate fault-bounded magnetic signature with these linear anomalies in here, and that's how we've redefined the extent of the Billabong complex. The granitic suites in the area, we touched on this a little bit in some of the other slides, but there's three main suites, being the Grimoire, the Frederick and the Birthday suite. So the Grimoire suite tends to have typically low magnetic signature here, and they're often surrounded by the more magnetic stratigraphy of the Tanami group. The Frederick suite are these more circular intrusions here, typically have a low gravity response and quite a moderate to high magnetic response, often with a cross-hatched or concentric texture associated with them. Whereas the Birthday response has a signature sort of in between the two different suites, tends to have a low to moderate gravity response and a moderate magnetic response with a more smoother texture compared to the Frederick suite. I'm now going to hand over to Helen, who's going to talk a bit more about the structural interpretation that we've produced in this area and focus on a few key areas.
Thanks, Teagan. So in this portion of the talk, I'm actually just going to highlight some of the key structural relationships that we defined from the interpretation of the geophysical data. And I'll focus on three key areas and the overprinting relationships we see in these three areas in order to define a structural framework for the region to help us understand the deformation history of the Tanami region and the northwest Aileron Province. So looking in the Kumarian Frankinia Dome area, one of the major structures that we see, or the earliest structures that we can define or resolve from geophysical data, is characterized by these north-east dipping thrust faults. They're associated with the development of thrust ramp anticlines that plunge both to the southeast and northwest. They're associated with the development of very low angle thrust faults, developing parallel to the magnetic strata within the region. In this area here, we can actually see the refolding of F1 folds by both northeast to northeast striking F2 folds, as well as approximately north-south to north-northwest striking F3 folds, which plunge towards the south. So within this region, you get a series of complex fold over printing relationships, which we've had to unravel to devise the structural framework for the area. And then between these two major domes, you also have the large F5 synform, and I'll go through the other deformation events associated with this nomenclature in the other areas within the interpretation area. The latest deformation event within the area is characterized by these major west-northwest striking strike-slip fault zones. Here we see dextral displacement of both magnetic strata, major fault structures, and the truncation of earlier fold hinges. Whereas if you look in Mount Solitaire, again, we see type 2 fold interference patterns. Here we've got type 2 fold interference pattern associated with this refolded F2 fold, which is refolded by these east-west striking F4 folds. Here we can see our earlier northwest striking F3 folds now plunging to the northwest. So you end up with very complex fold over printing relationships. And here what we can see is this latest folding event characterized by very open, long wavelength folds here plunging to the northeast. And that fold hinge is subsequently truncated by the latest transcurrent deformation event here associated with sinistral displacement. The other thing I wanted to highlight about these structures is that often in F2 and F3 fold hinges, you get the intrusion of these smaller rounded granitoid suites that truncate earlier F1 folds. And here you can see they develop small contact metamorphic aureoles. In the Dead Bullock Soak area, so this is the area most proximal to gold mineralization within the Tanami. You can see from this structural interpretation that we have these parallel low angle thrust faults associated with F1 fold hinges here. The plunge of these folds and the fold geometries themselves are less apparent than they were in the structurally complex area between the Frankinia and Kumari domes. But you can see these thrusts and fold hinges being refolded not only during D3, so associated with the north-northwest striking folding, but also you can see their more prominent folding during later deformation and the generation of these northeast striking F5 folds. And characteristic of much of the area within the Tanami and northwest Aileron, you can see relatively abundant minor offset along late brittle faults. So just small amounts of displacement along later fault generations. We did a brief comparison of the structures and structural framework derived for the Tanami region to the extent of these units on the WA side of the border. So here we've got the Stubbins Formation, which is the equivalent of the Dead Bullock Formation, and then the overlying Kili Formation. So those turbidic origin sediments, they're here in yellow. But when you look at the fold interference patterns and cross-cutting relationships within the Stubbins Formation, again, what you see is the very early generation of isoclinal F1 folds that are overprinted by a number of different other fold generations, including these northeast striking F2 folds, north-south to northwest striking F3 folds, and then you have these later chevron east-west striking F4 folds that tend to only be locally developed. And then the major architecture again is overprinted by these very long wavelength northeast striking, northeast plunging F5 folds. And then the final deformation event characterized by significant strike slip displacement along west-northwest, south-southeast or northwest-southeast striking strike slip faults. So you see the same structural framework both on the WA side and in the Northern Territory side. As part of this study, we also developed a series of forward models in order to look at the subsurface geometries and distribution of the major lithologies as well as the different faulting relationships. These cross sections were modelled relative to seismic sections or seismic profiles, including this northwest striking T1 profile. And you notice that the seismic profile does deviate somewhat from the forward model profile. So there is small differences in terms of matching the surface geology, but they're relatively consistent. The seismic models were, or seismic data was acquired by GA 2005. One of the major interpretations of this data done recently was by Golby et al. In 2009. So we aimed to integrate both the seismic data and potential field data to look at this fault architecture, differences in unit thickness, the presence of any repetition of units to better understand deformation mechanisms or characteristics. And then also look at the units of the Tanami group, including dead Bullock and Callie formations, to compare to these earlier interpretations. So looking at the T1 forward model here, we have a profile of the magnetic data as well as the gravity data, which does cross the Willaura gravity ridge. And these were used or modelled to generate these sections. And down here we have a model of the density for each of the polygons associated with the units depicted in this forward model, as well as the magnetic susceptibility down in this lower portion. And what I wanted to highlight from this forward model is coincident with the Willaura gravity ridge, is the south to southeast dipping boundary between the Aileron Province and the Tanami Region. Again, this is consistent with the findings of Golby from 2009, as well as the unlapping or draping of the Tanami group over this major crustal boundary. This is just highlighting the different or the similarities and between the forward modelled petrophysical data that's constrained by, or the forward modelled geophysical data that's constrained by the petrophysical data that Teagan went through earlier, and highlighting the similarity in both the structures and the depth of the Tanami group depicted in the seismic data. So the major differences between this interpretation and that of Golby is that you do tend to see a deeper response modelled by the intruding Kumari and Frankinia granitoid domes, and it's associated with this zone of low reflectivity. Between the domes, you have an area of significant structural complexity, and within the modelled units of the Tanami group, we have the Mount Charles Formation here in the violet purple colour, which tends to occur in the lower regions of the Tanami group units. And then you've got Dead Bullock Formation in purple and Callie in this pale purple. Again, highlighting the nice correspondence between the structures, both modelled in the forward models as well as those depicted in the seismic data. The other forward model is this northeast southwest striking model. Again, we've got the magnetic response, gravity response, and derived forward models. We'll look at this model, this image just more closely and compare it to the seismic data. So one of the important features of this forward model is that we do note the occurrence of the Mount Charles Formation at depth within the Tanami group, and we have a repetition of the Tanami group units. So this implies or is associated with these low angle thrust faults that are subsequently refolded, and overprinted by cross-cutting faults. So we've got early unit repetition associated with low angle parallel faults, subsequent deformation. And this is again reflected in the two-way time seismic profile. And here we can also see a slight difference in the distribution or depth of the base of the Callie formation, just due to the deviation of the seismic profile relative to the forward model. These forward models were then projected into 3D space, or hung in 3D space. And what they really highlight is all of the different folding and overprinting relationships that you do or can interpret from the mapping efforts or structural interpretation of the potential field data. It is again reflected at depth when you combine the results of the forward modelling. So when we look at this structural history relative to the major deformation events characterised within the region, you have two events associated with the Tanami event at 1830 MA. So the first phase of deformation is characterised by those tight isoclinal folds, development of low angle thrust faults, and unit repetition. In general, it's recognised to occur in association with greenschist to amphibolite facies metamorphism, and is associated with south to southwest tectonic vergence. And then you have subsequent north to northeast striking tight to isoclinal folds associated with northwest southeast shortening during the second phase of deformation during the Tanami event. Following this, we actually have the deposition of the Ware Group. The Ware Group does not preserve evidence of these first two deformation events, but we do see fold overprinting relationships and fault overprinting relationships consistent with deformation attributed to the polyphase Stafford event between 1815 and 1790. So this tectonic event is associated with northeast southwest shortening, associated with approximately north-northeast striking to northwest striking F3 folds. And then you've got the local development of east-west striking chevron style folds under north-south shortening during the fourth deformation event. And then we have the development of those major northeast striking long wavelength folds during D5. And then finally, we have the transition to the brittle ductile deformation, transcurrent tectonism, and the major period of gold mineralization during the development of west-northwest striking dextral shear zones, northwest striking sinistral shear zones, and more rare northeast-southwest striking thrust faults, which we didn't touch on so much during this presentation. Finally, we had the deposition of the Pagi sandstone, and this deformation is just characterized by a very minor northwest striking strike slip faults, which offset the Calcagini suite and cross-cut those major granite domes. You also see minor doming of the Birundudu group, and they're associated, these structures are associated with north-northeast, south-southwest shortening sometime after 1735 MA. So the major conclusions of this study led to the development of a cohesive structural framework for the Tanami Region and Northern Aileron Province. We've provided a new interpretation or supported the interpretation of the Mount Charles Formation sitting within the Tanami Group. Revising the work of Golby et al., we have modelled the Frankinia and Kumari domes to have a greater depth extent than previously suggested. And as Teagan highlighted, there is that transitional relationship between the Tanami region and Aileron Province, indicated by the continuous geophysical response between the Lander Rock Formation and the Callie formations, which are generally regarded as lateral stratigraphic equivalents. So ultimately, the findings of this work have helped better understand stratigraphic relationships, correlation, and correlations, as well as the deformation events in the region. And ultimately, hopefully, it'll help inform the understanding of the assembly of the North Australian Craton during the Paleoproterozoic. In summary, by combining both new and legacy high-resolution aeromagnetic data, we've been able to unravel the complex geology of the Tanami region, despite there being extensive cover. And we've ultimately integrated both the available geological data and petrophysical data from the very sparse outcrop and drill hole databases available in the region. And from that, we've been able to create this solid geological map, develop this structural understanding of the architecture of the region, and ultimately better describe or define the geophysical and petrophysical characteristics of the major units within this region and their extent. So thank you all for coming and listening to Teagan and I today, and we welcome all of your questions at this point.
Great talk, Teagan and Helen, wonderful stuff. And we do have a couple of questions for you. First one is from the panel. Could you comment on the uncertainty in your geophysical interpretation and how this relates to the new structural framework?
I think when dealing with structural geophysics or the structural interpretation of geophysical data, what we can rely on are the overprinting relationships that we observe. Ideally, there will be geochronological constraints located along these major structures. However, there tend to be, well, they're actually quite relatively few in the area. There was work by Laura Petrella in 2019 who dated the initial phase of peak metamorphism at 1830 MA or 1840 MA, and then mineralization, so it was both vein hosted and parallel to strata, and that was dated at 1805, so that's consistent with gold mineralization occurring during the Stafford event. And then there's minor hydrothermal activity and fault reactivation at 1790. So her work is one of the few studies that actually allows us to constrain the timing of deformation. Do you have any further things to add?
No.
I think ideally, if you develop a structural framework from geophysics, you will either have existing constraints, or it can provide the basis for future geochronologically constrained metamorphic studies or mineralization studies as well.
Maybe just in regards to the modelling, I think, you know, this type of modelling, there's always going to be uncertainties associated with it, and what we've tried to do in this study is try and take the interpretation of the overprinting relationships that we've seen, observations from outcrop and any existing mapping in the area, and try and bring all that into the interpretation and bring that into the forward modelling. And we're really, I guess, testing our hypothesis or our understanding of what the geometries might look like against the gravity and the magnetic data, but absolutely recognising that there are uncertainties with that kind of modelling. And it's probably, there are other solutions that could put forward or that we could test. You know, we acknowledge that there are those uncertainties in there, but we've just tried to integrate all the data that we have in sort of constructing all these interpretations. Yeah, I guess it's just the standard problem of
having non-unique solutions to or within an area that has relatively sparse data.
Excellent, thank you. And that leads us to the next question about all integrated data sets from Ned Stoltz. Did you use radiometrics, and what about ASTA and other remote sense data?
Yeah, we had, so the radiometric data was acquired as part of this survey, and that was processed and it was looked at. But because of just the extensive cover in there, obviously it's only imaging what's at the surface. Most of the rocks that we're trying to map are actually not imaged in the radiometric data. So those data sets that just imaged what's right at the surface weren't, I guess, leaned on heavily in this interpretation in some areas, particularly where the Berrindudu basin was outcropping. That data was helpful and interpreted, but in terms of interpreting rocks of the Tanami Region and the Aileron Province, they're all undercover, and you just can't see them in those data sets. So it was mostly the magnetics we were relying on.
Understood, thank you. And what about the gravity? Esmail Asagi would like to know, what was the station spacing of the gravity data used over that area or in that area?
It's 4 kilometres across the Tanami area, with along some of those seismic profiles, there is 500 metre data as well.
So for the modelling, were you able to use the 500 metre gravity?
Yeah, so because our models don't exactly coincide with where the profiles were, so it was where it crossed, it's taken the highest resolution available, sort of where it's crossed, where the profiles crossed the grids.
Okay. And was there, so there, is there, I imagine there's some industry data out there. I haven't got into that part of the Northern Territory that much since coming to the survey here. Did you incorporate any industry data, or did you just rely on the government gravity data?
There was only a couple of industry surveys actually, so they were processed separately and I guess supplied as part of this data package, which will shortly be releasing. But so that was looked at in just a few sort of key areas where the data was available, but there's actually not a great deal of industry data, gravity data. Some of it's already actually incorporated into the NT database as well.
Another question here from the panel. Are you looking to update your interpretation when AusLAMP models become available?
Yep. I mean, absolutely. As you know, not just AusLAMP, and when the AM data is released for this area, you know, I think there are many aspects of these interpretations that can be refined, and I think we should be working with that data going forward to try and update this. Absolutely.
Great. And just final one from Ned Stoltz. What was the software that you used to perform the T1 and 2T profile modelling?
That was GMSIS in Oasis Montage. Yeah.
Thank you. I think that's all the questions we have for you. Terrific session. A few comments here saying that was awesome, and I agree. Thanks to all attendees, and keep connected through social media and the website, and we'll see you all for the next webinar on the 30th of this month. Thank you very much.
Thank you for having us.
Pleasure.